My name is Obremski, and today I'm presenting the paper Immersion, Attention and Collaboration in Spatial Computing, a study on work performance with Apple Vision Pro. Spatial computing is supposed to transform the way we work by seamlessly integrating virtual and physical spaces. The mixed reality continuum, introduced by Milgram et al., provides a framework for categorizing these technologies, ranging from physical reality to fully immersive virtual reality, with augmented reality and augmented virtuality in between. The Apple Vision Pro is an example of how spatial computing is evolving. Unlike traditional mixed reality headsets, it allows users to fluidly adjust their level of immersion, switching between augmented and virtual reality modes. This adjustability offers potential benefits for various work tasks. Fully immersive settings may enhance focus for cognitively demanding tasks, reducing distractions from the physical environment. Conversely, lower immersion levels might be more beneficial for collaborative work, where maintaining awareness of the real world is essential. Despite these promising capabilities, systematic research on how immersion levels affect individual and collaborative work performance remains scarce. To address this gap, we conducted an empirical study to investigate three key questions. First, does immersion level influence individual task performance? Second, does immersion level influence collaborative task performance? And, in relation to the new spatial computing device, the Apple Vision Pro, third, does the use of the Apple Vision Pro have negative side effects in terms of depth perception and user experience? Over the past decade, extended reality technologies, including virtual reality, augmented reality, and mixed reality, have advanced significantly. A key concept in this field is immersion, which refers to the extent to which a system surrounds and engages the user's senses. The mixed reality continuum proposed by Milgram et al. Serves as a foundation for understanding these levels of immersion. More recent work by Spatial et al. And Wienrich et al. Expands this concept, emphasizing the role of coherence, plausibility, and human perception in shaping user experience. Research has consistently shown that higher levels of immersion improve selective attention and cognitive performance. Studies by Cummings and Balanson, for example, suggest that immersive environments enhance focus by blocking out distractions, making them ideal for work settings like open-plan offices or co-working spaces. However, increasing immersion is not without challenges, particularly in collaborative tasks. Goodwin and Greenberg, along with Schroeder, found that immersive systems often obscure non-verbal cues such as body language and eye contact, making communication more difficult. While immersive environments can enhance the feeling of social presence, they may also reduce the effectiveness of interaction if facial expressions and subtle gestures are not accurately conveyed. Existing research primarily focuses on either fully immersive VR or traditional AR, leaving a gap in understanding how adjustable immersion impacts work performance. Additionally, little is known about potential side effects, such as whether spatial computing devices, like the Apple Vision Pro, affect depth perception after extended use, because it's still too new. Thus, our study aims to address these gaps by systematically analyzing the effects of varying immersion levels on both individual and collaborative work performance. We also examine negative side effects. These include depth perception and user experience. By incorporating both objective and subjective performance measures and potential side effects, we contribute to a deeper understanding of how spatial computing devices can be optimized for professional settings. Based on prior research, we formulated the following hypothesis. Higher immersion should lead to better selective attention. Higher immersion should improve performance in the spot the different tasks when performed alone. However, we also expect that higher immersion should reduce performance in the spot the difference task when performed collaboratively. This should be due to the fact that higher immersion should reduce social presence. Additionally, we explored whether depth perception is affected by prolonged use of the device and how users subjectively evaluated their experience. To investigate these questions, we designed a 2x3 mixed study with two independent variables: the level of immersion, 0, 50 and 100% as a between subjects factor, and the type of task, individual versus collaborative, as a within subjects factor. We used the Apple Vision Pro to manipulate immersion levels, utilizing its digital crown to control the transition between augmented and virtual reality. Participants completed the Stroop test to measure selective attention and a spot the difference task to assess both individual and collaborative performance. Regarding the manipulation check, participants should report seeing less of the physical environment as immersion increases, while their sense of presence should increase. 30 participants were recruited from a local university, with an average age of 22 years. Most had prior experience with digital devices, but not with mixed reality or spatial computing headsets. The study was conducted in a controlled environment designed to resemble a co-working space, complete with simulated street noise and visual distractions. Each participant first completed a baseline depth perception task and filled out a pre-questionnaire, followed by the main experiment. After completing the individual and collaborative tasks, participants again performed the depth perception test and filled out questionnaires on simulator sickness, social presence, and user experience. Let's now look at the key findings from our study. First, our manipulation check confirmed that immersion was successfully manipulated. Participants perceived less of the real-world environment with increasing immersion and reported a stronger sense of presence, supporting the validity of our experimental setup. Next, we examined the effect of immersion on selective attention. As expected, participants in the high immersion condition performed significantly better on the Stroop test than those in the medium and low immersion conditions. This aligns with previous research showing that immersive environments reduce distractions and enhance focus. For the Spot the Difference task, contrary to our expectations, higher immersion did not lead to a decline of task performance in the collaborative condition. In general, participants performed better in the individual task than in the collaborative task. However, that was only true for the low and medium immersion condition, but not for the high immersion condition. Additionally, as hypothesized, social presence decreased with higher immersion levels. Participants reported feeling less connected to their partner in the fully immersive condition compared to medium or low immersion. Finally, we found no significant impact of immersion on depth perception before and after the experiment, contradicting prior studies that suggested mixed reality might distort spatial perception. Additionally, qualitative feedback was overwhelmingly positive. Participants appreciated the headset's intuitive controls and responsiveness, though some found it heavy over time. Thus, we found no indication for side effects. Our findings highlight both the advantages and challenges of immersion in spatial computing work environments. For individual and collaborative tasks, increased immersion improves selective attention, supporting the idea that immersive environments can reduce distractions and enhance cognitive performance. This is especially relevant for work settings like open plan offices, where reducing external distractions is critical. Surprisingly, participants performed worse in the collaborative condition than in the individual condition. This contradicts research suggesting that teamwork usually leads to better outcomes. One possible explanation is that the specific task we used, Spot the Difference, did not fully leverage the interactive capabilities of spatial computing. Future research should explore more dynamic collaborative tasks that require deeper engagement and interaction. Additionally, while no significant changes in depth perception were observed, it remains an open question whether long-term use of mixed reality devices might have effects that only become apparent after extended exposure. Future work should use more interactive collaboration tasks than Spot the Difference tasks. Looking ahead, an interesting direction for future work is allowing users to dynamically adjust their level of immersion based on task demands. This could lead to more adaptive spatial computing systems that optimize both focus and social interaction. Additionally, longitudinal studies with mixed reality headsets should be conducted to evaluate the long-term effects on usability and workplace integration. To conclude, our study provides new insights into how varying levels of immersion impact work performance using the Apple Vision Pro. We found that increased immersion enhances user focus and cognitive performance for individual tasks, but can reduce social presence. This suggests that while immersion is beneficial for solo work, it may not always be ideal for teamwork, where subtle nonverbal cues are important. Additionally, we found no significant effects of immersion on depth perception after use, contradicting prior research. These findings have important implications for the future of spatial computing and mixed reality in professional settings. While spatial computing offers powerful tools for enhancing productivity, designing adaptive systems that balance immersion with social interaction will be key. Overall, this study marks an important step in understanding how devices like Apple Vision Pro can shape the future of work, bringing us closer to a world where digital and physical spaces seamlessly coexist.